So in this video, we're going to talk about how to solve 3x3 systems of equations using Gaussian elimination. So today we're going to continue learning about how to solve systems that look like this. This is going to involve us writing out an augmented matrix and then transforming it into row echelon form. Remember, what row echelon form means is that we have this triangle of zeros in the bottom left corner of our matrix. And remember, we discussed that how to do this is to perform row operations. So remember that there are three types of row operations that we can use to, transform our matrix. The first is row switching. We can also multiply a row by a non-zero number. And finally, we can also multiply a row by a number and then add it to another row. So we're going to use some combination of these three operations to transform our augmented matrix into row echelon form. So here's the example that we talked about, right? So remember we said that here's our original system. This is the augmented matrix, and then this is the row echelon form. And remember, the whole reason we did this is because if we take this row echelon form of the matrix and then we write out the system of equations, notice that it's much simpler than the original system of equations. So this will be one that's, easier for us to solve algebraically. So now today, let's fill in that missing step, right? So how do we do this? How did I go from this augmented matrix to this matrix in row echelon form? Well, like I told you before, it's row operations, but I haven't actually showed you the row operations until now. So now let's finally solve this mystery and see what row operations led to this transformation. So whenever you're doing row operations, there's no specific rules that anyone's written out, here's how to do them. It's kind of like there's general ideas that people use, like strategies, just from practicing with working problems. So one thing that I found is helpful is to focus on making the zeros in the first column first. Okay, so whenever I'm starting one of these problems, I always say that's my first goal, is to somehow make 2 zeros in column 1. And then I go from there. Because if you think about all the numbers all at the same time, it can get really confusing. Okay, so you want to focus on one thing at a time, one strategy at a time. And then as you work on it, the rest of it will kind of start to fall into place. It's kind of like solving a puzzle sometimes. Okay, so let's start off with our original matrix. Okay, so I'm just going to copy it here. So we have 2, 1, negative 4, and then 7, 2, 4, 2, 40, and 6, negative 2, 4, and 44. Okay, so my first step, like I said, is I want to form 2 zeros in column 1. Okay, well, if I look at my column 1, notice that I have, 2 2's, right? So I'm thinking that I can use one of these 2's to cancel out another 2, right? I just have to turn it into an opposite. If I have a negative 2 and a positive 2, I can make 0. So I'm going to use that idea. I'm going to do negative R1 plus R2. So remember that this means that my R2 is going to change. So I'm going to first start off by writing in the rows that don't change. So my row 1 and row 3, I copy down first because those are going to stay the same. Okay, so now I'm going to do negative R1 and add it to R2. So to keep myself on track, I'm going to write out what negative R1 is. So that's going to be negative 2, negative 1, 4, and negative 7. Okay, so now every element of R2 is going to get added to these numbers before I write it down. So 2 and negative 2 is 0. 4 and negative 1 is 3. 2 and 4 is 6. 40 and negative 7 is 33. Okay, so you see I've, partially worked towards my goal, right? I have 1 0 at least in column 1. Okay, so now to make the second 0. Well, if I look at column 1 now, I see I have a 2 and I have a 6. So if I can turn this 2 into a negative 6, I can get this 6 to become a 0 also. So the way to do that is to multiply row 1 by negative 3 and add it to row 3. Okay, so when I perform this transformation, I'm going to first write down the rows that don't change. So row 1 will stay the same and row 2 will stay the same. And my row 3 is going to change. So I'm going to change it. So I'm going to write out what negative 3 R1 looks like. So that's going to be negative 6. 1 times negative 3 is negative 3. Negative 4 times negative 3 is 12. 7 times negative 3 is negative 21. And now let's add these to the elements of row 3. So 6 plus negative 6 is 0. Negative 2 plus negative 3 is negative 5. 4 plus 12 is 16. 44 plus negative 21 is going to be 23. Okay, so now you can see I've, gotten partially the second entry in my last row into a 0. Okay, so, if you're suddenly looking at this, you may think, oh, well, I can multiply this first row by 5 and then add it here. Well, think about that. If I multiply this first row by 5 and add it here, I will get a 0 here, but I'm going to undo work that I already did, right? Because if I multiply this 2 by 5, it'll become 10. And then if I do 10 plus 0, well, then I have a 10 here and a 0 here. So you don't want to do the operations in a way that you undo something that you've already done, right? So we wanted to have 2 zeros here. So I don't want to undo any of my zeros. So I need to figure out another, kind of set of steps that I can take. Well, what's really helpful is sometimes to have your rows like as reduced as possible. And what I mean by that is like if there's a common factor you can divide out from one of the rows, it's a really good idea to go ahead and do that. So for example, I notice here in row 2, all of these terms are divisible by 3. So what if I took this matrix and I multiplied row 2 by 1/3? Okay, so that's the same thing about dividing by 3, right? So I'm just going to divide everything in row 2 by 3. So remember, once again, that means my row 1 and my row 3 are going to be unchanged. And so I'm going to go ahead and write those down. And so that's going to give me 0. 3 times 1/3 is going to be 1. 6 times 1/3 is going to be 2. 33 times 1/3 is going to be 11. Okay. So right now it may not really make sense why I did this, right? It just looks like I saw a bunch of numbers divisible by 3 and divided by 3. But the nice thing about doing this is, well, let's see. If I take this row, okay, since the first entry is 0, if I multiply it by 5 and add it to my third row, you see how I'm not going to undo any work that I did, right? Because 0 plus 0 is going to give me 0. So that's why I kind of went through that extra step of reducing this row. And so that's why it can be helpful when you're doing these problems to be on the lookout for like, those GCF type situations where you can, divide out a common factor. So now I'm going to do just what I told you I was going to do. I'm going to do 5 R2 and add it to R3. Okay. So remember in this process, my R1 and R2 are going to stay the same. And so let me go ahead and write those down. And let's transform now our R3. So we need 5 R2. So I'm going to start off by writing out 5 R2. So I have 0. 1 times 5 is 5. 2 times 5 is 10. 11 times 5 is 55. And now I'm going to add R3 to that. So we have 0 plus 0, which is 0. Negative 5 plus 5. And now we have that 0 that we needed. 16 plus 10 is 26. And 23 plus 55 is 78. Okay, so now one last step, because notice that when we have our matrix in row echelon form, that this term right here, there's actually 1. Okay, so we need to make this 1, and the best way to do that is just to divide by whatever number this is. Okay, so since this is 26, I need to divide everything by 26, right? And remember that the way to do that is we say 1 over 26 times R3. Okay, so I'm going to write down row 1 and 2 because they're not changing. And let's see, we have 0, 1, 2, and 11. And then 0, 0, and 26 times 1 over 26 is 1. And then we do 78 times 1 over 26, which is basically 78 divided by 26, and that's how we get 3. Well, we already did this part, right? So we took the augmented matrix, we transformed it to row echelon form. So like now what? Right now what we're going to do is we're going to take this matrix and write out the simplified system. So you can see the simplified system is 2x plus y minus 4z equals 7. And then we have y plus 2z equals 11. And then we have z equals 3. So what we do now is we take that z equals 3 and then we plug it back into this equation. Okay, that's why it's called back substitution. So we plug that in, and what that's going to let us do is solve for y. Because we're going to get y plus 2 times that z, which is equal to 3, and that equals 11. Okay, so that gives us y plus 6 equals 11. And now we know how to solve this for y, right? We just subtract 6 from both sides. And so we did y equals 5. Okay, so now we have two variables, right? We have z equals 3, y equals 5. So now we go to this first equation. So we have 2x plus y, so y is 5, and then minus 4, and then z is equal to 3, and that is equal to 7. So now let's just simplify this and solve for x. So we have 2x plus 5 minus 4 times 3, which is 12, and that's equal to 7. So we have 2x plus 5 minus 12 is going to be minus 7, and that's equal to 7. So now when we solve for x, we're going to go ahead and add 7 to both sides. So we add 7 to both sides, and that gives us 2x equals 14. And then 2x equals 14, we're going to solve for x by dividing both sides by 2. So when we divide both sides by 2, we get x equals 7. Okay, so now we can finally put all these pieces together, and we have our solution, which is 7, 5, 3, our ordered triple. Okay, so that's all the steps you need to solve this system using Gaussian elimination.